Okay. So just to make sure you can see that, and you can see my whiteboard. Yes?
Yes.
Okay. So just want to introduce the people that have contributed to the current version of this. So you see picture of me, then there's the next one is Reza Isani. He's a doctoral student at the U of A. Roy was one of my past PhD students and is now at Oklahoma, correct, Roy? He's there.
UNL, Hoshin.
Sorry, Lincoln, Nebraska. Sorry, I get confused between those two. And then Uwe Ehret, who you all know, and Marie, who's my spouse, but she's actually getting a degree in statistics. She's working on her PhD in statistics at the UOA right now, after having done a PhD in biology. And so she's also contributed to this. Oops. Okay. So the problem is how to infer entropy from a random sample. And here's the take-home message. Estimation of one-dimensional entropy from samples is challenging. I think we all know that. Bin counting can be highly unreliable, has large bias and uncertainty. You may not know that. I'll try to show you that and why. Sampling variability has to be accounted for. The main problem is estimating the underlying PDF shape. It's necessary, but it's also challenging. And I'm going to introduce a method based on estimating quantiles rather than bin probabilities, which shows considerable promise. Can try to show you why we think that. And the main thing over here is it does not involve counting bins, okay? It's a binning method, but it doesn't involve counting numbers of samples in bins. And that's the major difference, I think. And hopefully a contribution, I'm not entirely sure. We've tested this on Gaussian exponential log normal and a bimodal Gaussian mixture distribution so far. We haven't done exhaustive testing, so I'll show you results for that. Shows that you can get accurate, unbiased, within 1% and precise estimated entropy using relatively small sample sizes. We can use bootstrapping, and bootstrapping we've shown gives you a pretty good estimate of sampling variability uncertainty. And the main difference, the other main difference between this and bin counting, of course, there are other methods based on kernel density approximations and so on we haven't tested against. But the main thing over here is there is no hyperparameter tuning necessary or may not be required. Okay, and that makes a big difference. And we're working on a draft of the paper you've seen. Hopefully some of you have seen it. And the goal is to post that on Arvix along with the code so other people can try it and test it. And possibly submit this to Entropy Journal or someplace else if people have a better suggestion. Okay, the history of this is back in the early part of this decade. Gong Wei came as a PhD student to work with me at the U of A from China, and he introduced me to the whole information theory context, and we worked on estimating entropy and mutual information. And the point over there was to try to quantify aleatory epistemic information loss in models. Then in that about the same time when we had our ITG workshops in Germany and Santander, I remember discussing clearly with Uwe and others, Stephen and others, that we need to come up with some robust method for entropy estimation and some kind of protocol for doing this so that we could compare results from one person to another. So in about 2016, I started looking at this problem with Roy, based on the idea of using quantile spacings instead of a constant bin width. And then we worked on that a little bit. We had some challenges. Then Roy graduated, went to UNL. But this was a sort of an extension of a paper we worked on, which is now in EMS, where we were trying to deal with the problem of when you've got limited data samples and you're trying to estimate the extreme quantiles, so you're trying to get the confidence intervals, you need to estimate the position of the extreme quantiles. And so part of the motivation for this sort of came out of doing that. That paper actually has been published in EMS, and it involves making a correction to the quantile positions, the quantiles estimated from your data to account for the sample size. So if you've got small samples, you have to inflate those confidence intervals to have some, to not underestimate the confidence intervals. And then in 2020, I started working with Reza on developing an approach to sensitivity analysis based on information theory. And in doing that, we found bin counting to be extremely unreliable. So we were testing it. So that motivated this. And so we then resurrected the work, and this is what we're going to see here. Okay, so entropy is defined as expected surprise. When it's discrete, this is the normal formula that most people use, where n is the possible number of states. So you basically calculate the probability, multiply it by the log of the probability, take negative, and add it over the number of states. So for discrete, this is relatively simple. It's well defined. You identify the number of possible states. That defines your possibility space, count the number of samples falling in each state. This estimates the likelihood subject to sampling variability. And then use this estimate your probability as the number of samples in the bin to the total number of samples, and then compute the entropy using this standard equation. Yeah. When it's continuous, it gets more complicated because there are several things you have to do. You have to identify the range of possible state values. You might know this beforehand, in which case, no problem. But when you have data, you often don't. For streamflow, you might only know the minimum, 0. You might know the maximum, okay? You've got to estimate the form of the underlying data generating process. And then you need to plug those into the formula to calculate entropy. So estimating the form of the data generating process from samples is the major challenge here. And then the method we use to calculate entropy once we've estimated that form. Okay, these are the two questions we've got to deal with. Actually, we got to deal with all three because we've got to identify the range too. And that becomes important, as you'll see in a minute. So this is called differential entropy. And let's say we decide to approach this using a piecewise constant approximation. So we assume that P is constant equal to Pi on some interval, in which case, if we know the total mass of the interval, we can divide by the width of the interval to get the density. We can plug that into the equation, do the math, and we get an equation that looks like this, which is two terms. The first term is where capital P is the probability mass, small p is density, right? So the first term is discrete entropy, which is always positive, and the second term is the expected value of the log of the bin spacings. So I'm using a generic bin spacing. I'm not assuming constant width, right? So whatever the bin is, if you know the probability mass in that bin, you take the expected value of the log, okay? So the first term is always positive, and the second term, remember we're working differential entropy now, right? A continuous probability distribution just happens to be piecewise continuous. The second term, when delta becomes small, can become negative. And that's why differential entropy goes from negative infinity to plus infinity, okay? So now if we set the bin width to be constant, this is what we do in typical frequency histogram binning, that log delta x becomes a constant, you integrate over p, you get 1. And so this log delta x is the correction that you have to apply to the discrete entropy equation to get this differential entropy. And this approximation becomes better and better as delta x becomes smaller and smaller. And so for small enough delta x, this is that correction. And as delta x goes to 0, log delta x is negative and goes to negative infinity. Okay. So instead, consider the case where instead of having constant width bins, we use constant probability mass bins. Okay, that's what I mean by quantile spacings. Quantile spacings are spacings that give you constant probability mass. So you can plug in, let's say you've got n bins, you can plug in the probability mass is 1 over n, and you get this equation instead. So now you have log of n plus the average bin width, log of the bin widths. And you see that the first term there is the entropy of a discrete uniform distribution. It's always positive and increases with n. And the other one is giving you the effect of shape, right? It's the correction to a uniform distribution that you have to apply in order to to take into account the fact that you are not a uniform distribution. So it's the average log of the bin spacings, bin widths, okay? And you can go through some math and convert this to this form, which basically says that differential entropy is the log of the range. So that's, if you had a uniform distribution, it's the log of the width of that distribution between the minimum and maximum values, plus the average of the average of the log of the ratio of the bin width if you assumed constant width spacing, the same number of bins, so equal width bins, to the actual bin width that you're actually using. And if you're using width binning, you can see over there that those terms all become 1, and this thing goes back to a uniform distribution. Right? So in log probability. Yeah.
Hoshin, may I briefly jump in with a question?
Yes, please.
While you were working on this, have you developed an intuition about the interpretation of negative entropies? Like it must mean something like something you should forget until you are certain of some things. If we interpret positive entropies as questions we are short of before we have knowledge of something, do you have a good explanation of what negative entropies are?
Not off the top of my head just now.
Okay.
Sorry. But I will think about that. That's a great question because it might have some bearing on this equation here.
Maybe one quick comment on that. Like if you would change the unit in which you measure the variable x, then you would it could change from negative to positive.
That's true. But it won't take away the fact that it still goes to negative.
Yeah, but I mean, maybe then it's a bit unlikely that there's some fundamental interpretation of it if it depends on a change of unit. But that's my gut feeling about it.
Right. I think also you have to realize that in practice, we're dealing with finite precision. And so this problem of going to negative infinity has something to do with the fact that you're trying to do infinite precision, which is not actually possible in practice. Okay, so in log, thanks, Sui. So in log probability areas, the quantile space bins are wider than the EQ bins. Okay, so the terms are negative and you have to add entropy. And in high probability areas, the QS bins are narrower than the equal spaced bins, so you subtract entropy. But on balance, we're going to have more bins where the quantile spacing bins are narrow than the equal width bins, and so the net effect is to subtract entropy from the uniform density, and that's why you get the uniform density as being the maximum possible. Okay. So here's the general equation. Here's the equation if you do constant bin width, and here's the equation if you do constant probability mass. And we're going to do the last one. We're going to compare the second and third, but I give you the general one in case you want to come up with a different kind of binning strategy, right? This allows you to apply that. And we're going to use this form where you just take the log n over inside the summation. And the reason we're going to do that is to avoid numerical problems, right? So as delta x becomes small, n becomes large, so you don't have a problem of trying to take logs of very small numbers, very large numbers. And theoretically, this is going to converge as you increase the number of bins. You can show that the Kullback-Leibler divergence, so this goes to 0. And here are some numerical results using a theoretical density, using an approximation based on quantile spacings, where we put in a number, we just choose a number of quantiles, and then we use piecewise constant approximation and actually calculate that. And you can see that for the normal, exponential, log normal, and uniform distributions, you can see what that looks like. If you have too few quantiles, too few bins, you have positive bias. And as you put in enough bins here, something like 500 plus all the way up to 10,000, the bias goes away. And so this converges to the true theoretical entropy, which we happen to know for these distributions. And in the quantile spacing, you can see if you do it on a log y-axis there, okay, this is deviation from true entropy in percent. You can see it's almost linear. So it's this sort of an exponential, and that I think it's actually linear, but there may be some numerical problems why it's completely linear. Okay. To the 0 over there is 1, which is 1%. Okay. So the y-axis is just the Kullback-Leibler divergence over the entropy times 100. Okay. That's using the true quantiles. We know what those are. We can calculate them. Okay. And you can see by about 50 bins for these three, we've gotten within 5%, and with 500 bins, we've gotten within 1%. And here's what it looks like if you do constant bin widths. And you can see that it's actually more efficient for some distributions to use constant bin widths, but for the skewed distribution like a log normal, it has slightly different shape. Okay.
Hoshin, can you hear me?
Yes.
Can I ask a quick question? So when you're trying to do this and knowing that continuous distributions have theoretically negative entropies, will this method estimate the negative entropies? Because there are certain parameters for a normal distribution which will actually give you a negative entropy, right? And if the parameters were chosen that way and you obtained samples from that set, would you be able to estimate the negative entropies with this method or not?
Okay. In principle, yes. Just bear in mind, it's in the paper, but you can always rescale your data to make sure it has a positive entropy. Okay, if you want to.
Fair enough. But I'm getting to the point that theoretically it is negative, right? Because you have.
Right. That's right. Yeah, no limitations that I'm aware of. Okay. So just be aware that what I'm plotting here is the bias difference divided by the values, right? So it's a percent error. That's why it's going to 0. Okay. So I'm not, in fact, what we did was we chose distributions and we scaled them to have entropy 1, just to have a convenient basis.
Okay. Got it. Yeah.
All right. The important thing is in these graphs is that there was no sampling, right? These are actual theoretical calculations using the two approximations. So we have P, we got Q, we can calculate Kullback-Leibler divergence. All right. So now let's consider the piecewise constant approximation.
Hoshin,
what we're doing is, yes.
Shervan here. From the previous slide, hi. If I understand correctly, so what I understand is that basically it's a way of binning which emphasize the slope of the shift. So when there is more density somewhere, that slope. So it should be more efficient than constant binning at the end of the day.
That's what I thought too, but these are empirical results. And so it has to do with the entropy part of it, okay? It's more efficient to use quantiles to estimate the shape of the probability distribution if you're trying to do something else. Yeah. But this seems slightly counterintuitive, but it actually turns out to be more efficient to use constant width binning for a small number of bins with the constant bin width method. But so this is not the problem. Okay, the problem is somewhere else, as I'll show you in a minute.
Okay.
In a minute.
Sure.
Okay.
Yeah, sure.
Okay, so this is if you know the locations. The problem is in practice, you don't actually know the locations and you know the probabilities, right? You know the locations and you know the probabilities. Okay, so that's what an equal bin width looks like. Here's our data sample. We've got the formula. What do we have to do? Specify the range. So now we're working with data samples. Choose the number of bins, divide the range into a number of bins, count how many samples fall in each bin, estimate the bin probabilities, apply the equation above. Challenges, we've got to choose the endpoints of the range. This turns out to be hugely important. Choose the number of bins and to get a sufficiently good approximation. And then we got to deal with sampling variability because counting can be very sensitive to sampling variability, especially in low probability regions. UBI, for example, has done some work where he says, what do you do when you've got zero probability? No samples fall in a bin, right? So they correct that by adding at least one sample. And then there are other methods for doing that that people have published. Okay. So especially, but not only for small sample sizes, accurately estimating the range can be difficult because you just got your samples to estimate the range. And in general, you know the range is going to be larger than the range of your samples because you've got only a finite number of samples. You got to choose the correct bin width. And as I said, in some bins, you can get 0 samples. So this can cause a lot of uncertainty. So I'm trying to illustrate here that when you calculate the probabilities, you have to account for the fact that these probabilities are uncertain. Okay. And this uncertainties can cause the bias to be large. It can also cause the uncertainty to be large. And there's an entire literature on how to properly choose bin width that people have published, which people normally use, the Scott bin width and various other things, which are all based on assumptions. So we want to try to do this without making assumptions. Okay. This is just about sampling variability, which means every time we draw values from a sample, we get a different set of samples. Any statistic we calculate from that is going to have a distribution, and that characterizes the uncertainty in your statistic, right? And you want to be able to estimate that, and bootstrapping is a common way of doing that. So our goal is a reliable estimate, meaning bias small. My target is less than 1%. And uncertainty is also small. So how do we estimate uncertainty associated with binning? Simplest is just take a 2-state case. I'm sorry, that should say P1 plus P2 is equal to 1. I must have been sleepy when I did that. And when we generate a sample, it either falls in the bin 1 or it falls in the bin 2, right? So it turns out this simple binomial calculation, the probability that k of the samples from that you select will fall in bin j is given by this binomial distribution. And if kj of the samples fall in bin j, you then estimate the probability as kj of n, kj over n, and you can calculate the expected value from the binomial distribution, and it's supposed to converge to the true probability as you would expect. But you get the uncertainty there, and it's given by p in times 1 minus p in, or p in times p out over n. It's binomial, standard, divided by n. And in general, people have shown that this can be approximated by a Gaussian distribution, not entirely, but mostly to order n, by Gaussian density, where the mean is at the true value and the standard deviation is given by that value there, okay? So here's where it gets interesting. Let me assume that I put 10,000 samples in each bin. I'm only concerned with the uncertainty associated with that one bin. If there are 10,000 samples in the bin, and I'm looking at different probability values, so 0.5 in the middle, 0.1 on the left, you can see that the uncertainty is quite small, okay? Ignore the red line. Basically, we're looking at the width of these distributions. Now I go down to 5,000 samples. Uncertainty is not too bad. 1,000 samples, 5,000, 200, 100, 10 samples, and the uncertainty covers almost the full range of the probability, okay, in the middle, and about half of the range of the probability near the ends. So small numbers of samples are just really give you very, very uncertain estimates of the bin probabilities. If I take that and I plot this on the entropy curve, the surprise curve, right? So the expected surprise curve, which is minus log p times p. So you got p on the x-axis minus log p times p on the y-axis. That's a conversion from probability to entropy, right? The weighted surprise. Okay, that curve looks like this. And here I've got the probability uncertainties for 100 samples in a bin, which is still quite large. Okay, the uncertainty down at p is equal to 0.1 in entropy is quite large. It's a little smaller in the middle, and it's again quite large at the end. So these uncertainties and probabilities can convert into quite large uncertainties in entropy. And so that's for 500 samples, still fairly significant. Here's a slide I stole from Uwe. He sent this to me, so I could use it. And he's tested many different binning methods. These are all bin counting methods, I believe. Uwe will correct me if I'm wrong. And what he's plotting on the x-axis is sample size. On the y-axis is the recommended number of bins. Sorry, Uwe, did you want to correct me?
No, I just wanted to say correct.
Okay, thanks. And you notice that only one of these curves is more or less linear, meaning that the number of bins is a constant fraction of the bin of the sample size. And that's this thing called Klopper-Pearson. And Klopper-Pearson binning, if I understand correctly, will correct me, is using quantile spaced bins, but still doing bin counting. Okay?
Yes.
So we come up with, yeah, okay. So you can see for the uniform distribution, 35% ratio, normal distribution, 60% ratio, bimodal distribution, about a 40% ratio. I just estimated these off these plots. That ratio is all over the map, depending on the shape of the distribution. Okay, so we implemented the constant bin width algorithm. We chose a theoretical PDF, drew a sample set the minimum and maximum values to be xmin and xmax to be the smallest and largest values in the sample. We know that's an underestimate. Choose the number of bins, divide the range into that many bins, count the number of samples, compute the entropy using this equation, and then repeat 500 times by drawing from the original theoretical density to study sampling variability, and plot the results as a function of increasing sample size. And so these curves are expected values, the averages over 500 samples. This is a Gaussian. Again, I got the percent bias on the y-axis, the number of bins as a proportion of sample size. So it goes from 0 to 100 on the x-axis. And you can see that the optimal number of bins as a fraction of sample size varies as a fraction of sample size for different sample sizes, okay? So you've got all the way from 100 samples to 5,000 samples, and you can see where it crosses the 0 line, and that varies, that fraction varies considerably. This is a Gaussian distribution for 5,000 samples I marked. And I've marked 5%, 10%, and 1% error there. Here's the log normal distribution for 5,000. Sorry. Yeah, there was Gaussian, there was exponential, and there was log normal. So quite a huge range in values, not only for sample size, but also shape of the distribution. And here's a plot where we calculate the optimal number of bins as a function of sample size in percent against sample size. And plotted this for 3 different distributions. The colors there indicate distributions, and you see the uncertainty. So this is to have no bias, right? So you can see that the number varies with form of the PDF, and the uncertainty is quite large for small samples. the number of bins goes down, the ratio goes down as a function of sample size, and the uncertainty goes down with sample size, which is what you would hope. Yeah. Okay. So uncertainty is large even for moderate sample sizes. So if you look at, let's say, a sample size of 1,000, you can see that the number of bins as a fraction of sample size is varying quite a bit, from quite small numbers to reasonably large numbers. Okay, now let's compare that to using quantile equal probability piecewise constant approximation. So this is what that approximation would look like. And so we've determined them using quantiles. Here's the method: specify the range, choose the number of bins, estimate the positions of the quantiles from the sample data. So now we're not doing bin counting, we're estimating quantiles. Compute the bin widths from the quantiles, plug it into the equation. No counting of bin samples, and assumes that all the bins have identical probability mass. Challenges: we got to correctly choose the endpoints of the range. We've got to choose a sufficient number of bins, and we need to accurately estimate quantiles to get a good PDF approximation, and we need to account for sampling variability. I showed you this graph already, so you know what this looks like. Theoretically, we know that this converges as we increase the number of quantiles. So here's the method that we implemented. Choose a theoretical PDF, draw a sample, set, again, to be fair, the minimum and maximum to the minimum and maximum from the sample. Choose a number of quantiles. That's analogous to choosing a number of bins. Estimate the locations of the quantiles using a method I will show you in a minute. It's a very simple, naive method. Set the 0 and n+1 quantiles to be the min and max. Specify the bin widths from the quantiles, and then use this equation. Repeat 500 times to study sampling variability. And here's the sub-algorithm. You draw sample NS points from the PDF. You choose a number of quantiles, and make sure that the number of quantiles you choose is smaller than the sample set. And exactly how small we'll tell you in a minute. Okay, how much smaller. Set the minimum and maximum. Now you take your sample set and you draw a subsample of values that is NZ long. So if I want to estimate 100 quantiles, I sample 100 points from my data set. I order them and allocate the first point to be Z1, the second point to be Z2, third point to be Z3, and so on. I basically just sort them. And that's my naive estimate of the quantile without really knowing what the quantile is. It's somewhere in that region. Then we repeat that nk times. So 500 times seems to work well. So we get nk sorted subsamples. Take each of these ones, take the first value in each subsample, put them all together, take the average, and that gives me my estimate of the first quantile, average the second point, that's the second quantile, and so on and so forth. And so just if you didn't get that way, here's my first sample, second sample, so on. I've taken the red point as the second point in that sorted order. Okay, it's got a probability distribution due to sampling variability. I'm sort of bootstrapping. It's not exactly bootstrapping, it's resampling. And I average those and I use that as my estimate of the quantile. Okay. So instead of counting samples, we're going to estimate quantiles and we're going to average over them to smooth out random variability. And this is just saying
Hoshin, I have a quick question.
Yes.
How many, can you go back to the last slide? How many total samples do you need to estimate the bins? So you're actually using the fact that you're repeating the sampling in order to estimate the parameter needed for the algorithm. Is that, did I understand correctly?
So I need to estimate quantiles from my sample data. So instead of, and if I've decided, let's say I've got 1,000 data points, but I want 100 quantiles. I'll tell you how many quantiles I need later, but let's say I want 100 quantiles. I just draw 100 samples from my 1,000 samples and order them, put them in a matrix, draw another 100. So there's no, with the replacement, right? So I just go back, resample, I'm treating my original data set as though it were the true distribution. And I keep drawing over and over and over again. And I'm going to get, for my first location, a bunch of different possible values. For my second location, a bunch of different, and I'm going to average those. So I'm basically smoothing, okay?
Do you know, does this actually give statistically convergent estimates of quantiles?
Only if the sample set goes to infinity. In general, it's going to give bias in the samples. I was going to talk about that in a minute. So especially near the extreme points, it's going to bias it's going to bias the estimate of the quantile towards the high probability side, because you'll tend to have more samples on the high probability side and less samples on the low probability side. Okay, but I'll show you it does converge. Okay. So as the number of samples increase, as the number NZ, which is the number of quantiles, increases, because the distance between quantiles is getting smaller and smaller and smaller, right? The bias in the estimated quantiles has to go down, right? And as the number of samples goes up, that's helping. But in general, you're going to have a slightly peaked density with a slightly lower entropy than the true PDF. Okay, and this is actually going to work in our favor, as you'll see in a minute. So we're going to get a distribution which is a slight lower entropy than the true entropy. Okay, it's going to be slightly squeezed and slightly more peaked. Okay, and there's a lot of literature on properly correcting quantiles, but we decided to use this naive approach before we went to a more sophisticated approach, and it turned out to be a good thing to do, as I'll show you in a minute. This is just explaining quantiles. And this is just showing that if you were to draw several samples from a distribution, these are Gaussian, gamma, and uniform, and if you were to construct the CDFs from those different, you can see how much sampling variability there is in the construction of the CDF, and therefore how much sampling variability there is in the shape of the distributions for different quantiles. Okay, so where it's steep, you tend to get more Gaussian looking distributions. Where it's curved, you tend to get more skewed looking distributions. And the top row is for 100 samples and the bottom row is for 1,000 samples. Just showing uncertainty goes down. But here's the plot that Gray is asking about. So I'm increasing the number of quantiles as I go to the right. I'm drawing from the parent population. So I'm doing this with an infinite sample size, essentially. And I'm plotting the deviation from the true quantile for 90%, 95%, and 99%. And I'm showing you how that deviation, that bias, which is negative, goes to 0 as the number of quantiles becomes large enough, and how the uncertainty goes down. Okay. So if you get enough quantiles, in this case, to get less than 1% bias, I need to get to about 1,000 quantiles or so. Yeah. Anyway, it just shows that it's converging, but it's negative. And that was for the log normal density. I just showed you one. Yeah. So, okay, so that's how we estimate the quantiles. Now, we also have to estimate the endpoints of the bin. And this turns out to be critically important. And this is showing you that. If I expand that summation, you'll see that I have a term which depends on the lower endpoint and a term that depends on the higher endpoint. And this is Z0 and Zn plus 1, right? 0 and 1 quantiles. And I don't know what those points are. This is the first bin, this is the last bin. In general, we don't know what these values are, but we know that as the sample size gets larger, X-min hat will tend to the true value and X-max hat will tend to the true value. But you can see that this term log NZ delta X1 and log NZ delta X NZ are very sensitive to the selected values of X-min and X-max. If you choose delta X-min such that delta X1 goes towards 0, then log of 0 is negative infinity. So you're adding a term that is negative infinity. If you choose delta X1 and delta XNZ, so it's 1 over the number of quantiles, that term becomes 1 and log of 1 is 0. So you don't add any term. okay? But if you make delta x too large, okay, presumably much larger than 1 over nz, you can drive h1 and hnz to infinity. So you can make your entropy any number you like just by changing xmin and xmax, okay? So that's a problem. So you need to estimate that. So we tried many different methods, and finally it turned out that the simplest thing to do worked in our favor, which is just take the minimum value of the sample and set that as my lowest zero quantile, and take the maximum value of the sample, set it as my largest value, because there's no way from the sample for me to know what the real minimum and maximum values are. So my simplest assumption is to just use the values from the data sample. And that again turns out to work in our favor. And if for a moment, if you want to argue that, oh, it doesn't matter what the end entropy is, it's not very large anyway, here's a plot of the true theoretical entropy fraction as a function of quantile bins for different distribution forms. And you can see that, for example, the log normal density at the bottom end, the end bin can be as much as 5% error. And for the exponential and normal, the end bin on the right can go up pretty large, okay? And you have to put a large number of quantiles before those percent entropy fractions go down sufficiently small to go away, okay? Okay, so here's the punchline. Here's the results. We're plotting estimation bias on the y-axis, number of quantile bins as a percentage of sample size on the x-axis. This is the Gaussian distribution for different sample sizes, repeated 500 times average. Each curve is the expected value. And the bias is positive in the beginning when you have small numbers of bins, as expected. And then it crosses 0 at some fraction, and then it becomes negative. Why does it become negative? Because of the things that I mentioned before. We have to estimate the quantiles, and we're slightly underestimating the density is slightly peaked. And we're using xmin and xmax, which are underestimating the entropy contribution of the end bins, okay? But the exciting thing about this is, look where they all cross. They all cross in the region of 20 to 30% fraction, okay? So this is the Gaussian density. This is the exponential density. And there's the log normal density. All cross at all more or less the same place. Here is the estimation uncertainty due to sampling variability as a function of sample size. The estimation bias in percent is given there. Again, I'm putting 1, 5, and 10% on there. And this is results using this ratio of number of quantiles to number of sample size is 0.25. So 25% of the sample size is what you're going to choose. We just chose 25% for this plot, okay? You can see that the bias is very close to 0, independent of the short shape of the distribution. And the uncertainty goes down as you increase the sample size. But notice that the sample sizes here are quite small, okay? You've got a sample size of 10, 20, 50, 100, 200, and 500. And the bias is very small and the uncertainty is fairly small by the time you get to 500 samples. Now, that was when I drew 500 samples from the parent distribution. What happens if I draw one sample and use bootstrapping to estimate the uncertainty? Okay, and repeat that many times. So if I do that, I can plot the ratio of the interquartile range that I get using bootstrapping to the interquartile range I would get if I actually had access to the parent population. Okay, so I'm plotting that ratio. And if bootstrapping is 100% efficient, I should get a ratio of 1. I should get the same uncertainty with bootstrapping as due to sampling variability as I would get using actual sampling variability from the true, if I sampled from the true parent population. And so here's the results for that for different sample sizes with the uncertainties. And you can see that it's pretty close to 1. bootstrapping tends to give you slight overestimation on average. And when you get to sample sizes of around 1,000 or so, the estimate due to bootstrapping is pretty good. It's pretty much the same as if I actually had access to an infinite number of samples sets. Okay. So here's the recommended procedure. Start with your sample set. Choose Xmin and Xmax as the minimum and maximum of the sample. Set the number of quantiles to be some alpha times the sample size, which is somewhere in the region of 0.25 to 0.35. Let me just go back to point out something I forgot to say, which is notice that it's more sensitive to alpha being smaller than to alpha being larger. Oops. So it's okay to estimate on the side of being slightly larger, but you don't want it to be 100% because then you've got other problems. Bootstrapping is your resampling is no longer getting independent samples. But you can see somewhere in there seems to be okay. So we, 0.25, 0.35, somewhere in there. Estimate the quantiles using the procedure, specify the bin widths, compute the entropy using this equation, and then bootstrap from your sample side. Repeat this many times, 500 times should work. And now you will have, and then you can plot now you'll get a distribution of your estimate, which should have very small bias and relatively small uncertainty, where the uncertainty depends on the sample size. So to summarize, the piecewise constant approximation gives you positive bias because the approximation is biased towards a uniform density. It's rougher. Yeah. The use of minimum and maximum tends to result in negative bias. The quantile estimation procedure tends to result in negative bias because the quantiles will tend to be squeezed towards the high probability regions. But the overall effect seems to be that they cancel out approximately at alpha is equal to 0.25 to 0.35. And unlike conventional constant wind binning, we don't need to do any tuning, therefore. We just choose this value somewhere in that range, set it, and we're home free, provided it holds for other distributions too.
Yeah. Have you tried any multimodal distributions?
You're anticipating me. I'm going to show you a result right now. So the main argument, I think the reason it works is because quantile space binning follows the shape of the PDF better. And this, I think, explains why alpha as a hyperparameter is not so strongly sensitive to the PDF shape. That's my intuition on that, but I'd be happy to hear other people's opinions about that. So I want to know if this ratio depends on skewness or the easily computable properties of shape, because if it did, we could actually come up with a relationship for it. Test more complex PDFs. We're just starting to do that. In principle, we're using piecewise constant PDF approximation. In principle, we could, with a little bit of extra effort, make this piecewise linear approximation. We haven't tried that. The equation is not quite so simple. In principle, because this is a one-dimensional problem, we should be able to extend this to apply this to estimate cross entropy and KL divergence in a fairly straightforward manner. It's not immediately clear how to extend this to multidimensional spaces, but if we could crack the problem of estimating two-dimensional mutual information, that would be really, really useful. So I'm thinking about that. And thanks for the question, Gray. Here's the bimodal distribution that we've tested on, just one we got result this week. So it's a mixture of two Gaussians, okay? It's not strongly bimodal, but so, we don't know. We have to test other distributions. Over there, in this case, I don't have the theoretical true density, entropy. But I can use piecewise constant approximation using the true quantiles of this distribution and increase the number of quantiles and drive it to infinity to get the Kullback-Leibler divergence converge to 0, and so get the true entropy. And so we've done that here. And so we increase the number of quantiles over there. And for this, it turns out that with 10,000 quantiles, So the true entropy is close enough to 2.265, okay, for this particular density. And here's the result. Run on that for the bimodal Gaussian mixture density for a sample size of 5,000 samples. And once again, you see it crosses nicely at 25%. And here you're seeing the uncertainty that you didn't see on the previous plots. Okay. And then I asked Reza to run that for different sample sizes. So 100 all the way up to 5,000, and again, it sort of crosses around 25 to 30%. Okay, 1% error. Okay, so now I'm showing you averaged over 500 repetitions. Okay, so this one is not averaged. This is the actual density. Question?
Hoshin?
Yeah.
The commonality of the distributions you use so far is that they're unbounded. You know, they go from minus to plus infinity.
Correct.
And that's why this, you know, these effects that you see can compensate for each other. Have you also tried for distributions that are really bounded for physical or other reasons? So one of the terms of the trade-off does not jump in.
So far, we've only tested for the log normal bounded on one side. But yeah, obviously we need to test this for a full range of other densities. And it's not clear which is the term that's contributing the most. Is it the X-min X-max thing, which is helping to do this, or whether it's the quantile estimation procedure that's helping to do this? I'll be the first to admit that this is if this result holds up, it's a very, it's a sort of a conspiracy of lucky things, right? It just happens that my method for estimating quantiles gives me underestimation that compensates for the overestimation and so on. All I can do is show you the results. Empirically, they work really well, but I don't have a complete proof or 100% explanation for why they work yet.
Even if it should only work for unlimited, unbounded distributions, it would be great. You know, that's a large class of distributions.
Sure. I have a feeling that it probably won't make a huge difference for bounded distributions. I think so, but we will test some and see what happens. But this I thought was interesting. Reza pointed this out. On the left is the Gaussian density estimation bias. On the right is the bimodal Gaussian density estimation bias. Interestingly enough, the estimation bias is smaller for the bimodal than for the Gaussian density at small sample sizes. Sorry, for a smaller number of quantile bins. I'm not entirely sure why that is. So there is something going on here that we still don't also understand. Okay.
Maybe it's because it's a bit closer to uniform in some sense, the bimodal.
Maybe. Oh, possibly. Yeah. Interesting. Okay. So this is just repeating what I said at the beginning. Estimation is challenging. Bin counting can be highly unreliable. Sampling variability must be accounted for. I think that the method of quantile spacing is a more efficient use of information in the samples than bin counting. Why do I think that? Because when I count samples in a bin, only the samples that fall in that bin are being used as a fraction of the total samples. Only those samples are being used to calculate the bin probability, right? So if 10 samples fall, only those 10 are being used. Of course, relative to the total sample. Whereas when I do quantile, when I estimate the position of the quantiles, in principle, all samples in the neighborhood of that quantile, however many they happen to be, will contribute to the estimation of that quantile. So my gut feeling is that it's a more efficient use of samples to calculate PDF shapes than doing frequency histograms. And then the rest is what I said before. Okay.
One question, Hoshin. Thanks for the presentation. I have a problem with using equiprobable estimation of entropy when I'm using it to estimate entropy for heterostochastic variable like precipitation, when we have like 30% of values is 0. So we cannot use the quantiles. So first bin would be 30% and the rest is equiproblem. I was wondering whether you had a solution for that or you have thought about it.
Well, if you have one bin, so what you've got is a discrete continuous mixture.
Yeah.
Right. And you can just separate that into two terms. Right, the contribution due to the discrete part and the contribution due to the continuous part.
Mm-hmm.
So in principle, what we're talking about here is just dealing with the continuous part.
Yeah. Thanks.
Yeah, Hoshin, I don't know if you finished answering the question, sorry.
Sorry? Sure.
I don't, did you finish answering the question? Can I ask a question?
I believe so. Was that a good enough answer, Hussein?
Yeah, it
okay.
It's continuous. You're working on continuous, and my problem wasn't discrete.
Well, yeah, but also what I was saying was that you're integrating, right? So when you integrate, it's a summation. So you can sum out the two terms, and you can calculate the entropy components of the two terms and add them together.
Mm-hmm.
Right?
Yeah, that's good.
Sure.
Yeah, so I'm just wondering, like this 20 or 30 basically percent of the bins that you are coming up with, and it's consistent across different distribution.
Yes.
How strongly it's related to the way that the program that you use is generating the samples. Because I remember from if you remember, we had some very preliminary work in 16 or 15, and there was an issue with MATLAB generating uniform samples. So actually the samples were spaced, in my point of view, like 1/3, 2/3, 1/3, 2/3. I mean, if you zoom out, it looks like uniform.
Okay.
But it seemed that they were not uniform. So there was some, I mean, we discussed this, there was creating some constant at the end.
I think what you're referring to, Shervan, is related to when I was trying to estimate the quantiles using the entire sample set without doing averaging. So if you take the entire sample set and you calculate the CDF, so you just sort the values and you make the CDF that way, okay?
Yes. Yeah.
And then you calculate the quantiles from that. If you drive the sample set towards infinity and you calculate the entropy that way, you will not get an unbiased estimate of entropy. And the reason you don't get an unbiased estimate of entropy is because you have always, doesn't matter what your sample size is, you always have roughness in your CDF. You always have sampling variability in your CDF. And I remember us talking about that, and Roy and I talked about that. And we found that contrary to our expectation, we would think as you run the number of samples towards infinity, that your CDF would approach the true CDF. But actually it doesn't.
Yes, so my question then is the results you are showing here.
So we're taking advantage of the law of large numbers, and we're averaging, and that average is removing that bias.
Okay, yeah.
So we're ending up with a smooth CDF, right, by sampling many CDFs and then smoothing them, and that averaging is removing the effect of sampling variability.
I see. Okay, but when you do it before binning, right? Or before quantiling?
And actually, I'm doing it during quantiling. So the act of using samples chosen from the sample set to calculate the quantiles is a smoothing operation. Okay.
Yes. But when you go to the higher number of bins, this smoothing goes away, and
right. And that's why you get negative bias. Yeah.
Yes, so that's why I'm saying that this transition from positive to negative that you see, and the points that they are passing, is it related to this sampling?
It's related to the fact that if you use the entire sample to calculate your CDF, you will get negative bias. And yes. if you choose the number of quantiles to be very close to the total sample size, your samples will not be independent. And so when you average them, you're not getting an unbiased estimate of the quantiles.
True. And may I ask, which program are you using to create these samples? Or do you think that it would be interesting to change, like, I don't know, do be totally different?
Sure. Reza could probably answer that question if he's still on.
Yeah, I'm here. We tried both MATLAB and Python, and both of them were working similarly.
Okay. Okay.
Yeah. Hoshin, one quick question.
Sure.
So the way you are doing that sub-algorithm makes me think whether this method would be applicable only for a unimodal distribution, or it would work equally well with bimodal distribution.
So we did this for this bimodal distribution, right?
Yeah, okay.
Here's where I think the problem will run into. Let's say that I have, actually, let me draw a picture. Let's say that I have a distribution which looks something like this. Okay. So I've got a very tall spike in a very small region with some significant, with a probability, it's a high probability density, but a very low probability mass. Now, when I sample points, it's going to be very, very difficult to get a sample that falls in that little spike. So the number of samples I would need to be able to do that accurately is going to be extremely large. Probably these are not typical kinds of things that we would run into, but I do think we need to test the method for various kinds of pathological distributions just to see where it falls down. But that intuitively, that's one place. Yeah.
Yeah, I mean, the idea is not to basically get bogged down by pathological cases, right?
I mean, another pathological case would be a distribution that looks like that, right? It's very rough. So we're talking about sufficiently smooth distributions.
Right. So what is your estimate as to difficulty with multidimensional student?
So the problem with multidimensional is that, let's say I've got this over here, right? I can do the entropy of X and I can do the entropy of Y. This is easy. The same method will work for X and Y, right? The analogy to a quantile in a two-dimensional space is not a point, but it's a curve, right? It's a closed form, whatever this thing is, the ellipse in this Gaussian case, right? So that's a whole different ball of wax. So we don't want to be able to do that. So the challenge now becomes is I can figure out how to do spacing in this direction. I can figure out how to do spacing in that direction. But that's not sufficient for me to characterize the cross entropy between X and Y. because each of these bins is just a uniform distribution, and there's no cross entropy in any uniform distribution bin, right? So how to crack that, I thought I'd cracked it, because if you plot this in, you could say, well, actually entropy is equal to 1 over the number of bins, sum log number of bins times you could say it's the area of the bin in this case, right? That would be the analogy to the width. But that actually doesn't turn, so in other words, area would be delta x times delta y. But if you do that, all you just get is hx plus hy. So you're not actually calculating cross entropy. So, I mean, I've only thought about this for one day so far, but I'm a little bit, I got very excited. Oh, we could do this because, in some places delta x will be small and delta x will be large and so on. But then when you do the math, no, it just gives you the sum of the two entropies. So I'm missing something, and I don't even know if it's solvable, but it's worth trying.
Okay.
I mean, the way we can do it would be to, but you run into sample issues, but maybe it may be the only thing we can do, which is like this. The naive thing to do would be, so I choose a width of x, and now I take all the samples that fall in this region, I project them over, and now I've got samples and I can calculate h of y for that delta x. And now I can do that for different bins, right? But let's say I've got 10,000 samples here. In each one of these regions, I might have only, let's say, in the worst case, let's say I get down to 25 samples or something like that, right? This is the direction in which I'm thinking that maybe we can solve the problem. Because now I can estimate entropy for this, and I can subtract that from entropy of the whole sample. And now this gives me h of y given xa. And then I have to do the expected value of I have to do h of y minus the expected value of y given x, where this is xa, xb to x, whatever, m, whatever the different, these different bins along here. And that gives me mutual information. But now I have to account for the fact that each of these estimates is going to have a different level of uncertainty, right? Because I've got different numbers of samples in each vertical stripe. So there may be a way to approach this. But of course, number of samples will have to go up.
Okay, until you solve that problem, we'll have to live with our fixed bin method, Hoshin.
Okay. Yeah, for now, that's the only thing. Oh, but there is one thing that I might recommend, Praveen. And that is use fixed bin method, but bootstrap from your sample when doing your fixed binning and average.
Yeah. Would you be able to go to your slide 41?
Sure. Let's see, maybe faster. Oops, no, okay. Yeah, I think I have to go to my PowerPoint. Nope, come over here. 41.
Slide number 41 on the bottom right.
I'm getting it, yeah. Yes.
Right, so in this thing, I mean, you have to decide on how many samples you take, right? So yes. Here you have NK different samples. And as you rightly show that there is a PDF associated with that average. Yes. Now, I'm wondering whether that NK is determined by so some confidence interval saying, hey, the exceedance probability 5% or something, and basically you have a control on that in there, and then determine the number of those by that method.
Well, NK is basically controlling the precision of your estimate of the mean, right? When you have the mean, you know that it goes down as 1 over square root of NK. So with 500, you can tell how precise that estimate of the average is. 1 over square root of 500, approximately. Yeah.
So another thing is, I mean, one of the challenges we face is low sample size. I mean, for some of the things that we are doing, I think 500 is a luxury to have 500 sample size. I mean, with
Sorry. Oh, yes.
No, I understand it doesn't have to be 500, but one of the things which we struggled with with Allison was trying to get down to being able to estimate entropy and other things with maybe 200 sample points total. So how does, might have missed it, does it compare well or better than the fixed bin method at very low sample sizes?
I'm trying to find the slide. Yeah, so here's the plot that you want there. So for 200 sample sizes, we're getting bias of less than 1% and uncertainties of less than 5%.
Okay.
I actually have a question about this figure as well.
Sure.
So when you do this for this figure, you are drawing 10 new samples from just the parent distribution. Have you done it where you do 10 new samples or whatever number of samples from an already sub sample?
So that was the next plot, which is the bootstrapping plot.
Right.
So now I'm drawing the samples from the sample set, not from the parent distribution.
So have you compared this to either bin counting or any other of the methods?
No, and that's what I was proposing to Praveen, that if you're going to use bin counting, get a little bit smarter and bootstrap, and then estimate your probabilities by bootstrapping. Don't just use a single count. I haven't done that. We haven't done that comparison.
Cool. Yeah, and I also had maybe more of a speculative question also on slide 41. So you basically have these little subsamples which kind of get at finding out where, on average, like sort of pieces of density come from.
Yes.
It seems it's. I almost wonder if there's like a relation of this method to like a nearest neighbor type method that's sort of like hidden in the
Sure.
in the math somewhere.
Yeah, we're doing a combination of something like bootstrapping. It's not bootstrapping, it's resampling, right? Because bootstrapping you do without replacement. And typically this is bootstrapping with replacement in a sense. But the nearest neighbor is definitely playing a role, because as you increase NZ, then you're actually squeezing it in from both sides, right? So the estimate has to get better and better because it has to be between this value and this value. And so you're getting the advantage of a kind of a nearest neighbor approach, which as you increase the number of points you sample, it forces your value to be more and more precise. Yeah.
So speaking of that, oh, sorry, whoever was talking can go ahead.
No, Allison, go ahead.
Sure. So speaking of speculative questions about building a better PDF, I was wondering, like this kind of made me think of, like different ways to choose the thresholds of your PDF. And what we talked about a few of these meetings ago had to do with rate distortion theory. And I think it was like in the information bottleneck. And I've kind of started thinking about that as basically a procedure to, in determining those thresholds of your data set that minimize the distortion of making the assumption that you have like a piecewise linear thing like you mentioned. I wonder where this quantile method falls in terms of the range between fixed binning and something like that, because it seems like something like this that's kind of what you're doing is you're minimizing, you're somewhat lowering the distortion of having chosen a certain representative value within your PDF.
Actually, that's great because thank you. I hadn't thought of it, but you put it really nicely because I was talking about information bottleneck to my class today. And I was pointing out that what information bottleneck is doing is asking what's the minimum number of features, the minimum number of features you can get away with in order to predict your quantity of interest, right? So your quantity of interest is the relevant variable, and here entropy is the relevant variable. And so it's turning out in this case that the 25%, so 75% compression is essentially giving us the right amount of compression in order to estimate entropy.
Okay, that makes sense. The 25 threshold, like if it were 100, that would mean that you might as well consider every single spacing. Okay.
Right. The problem, but it's interesting you mentioned that because this is a problem in the information bottleneck that they pointed out in that paper by Goldfield, which is, let's say I've got 1,000 samples, and I'm trying to estimate entropy from 1,000 samples. I can start with one bin, right? And therefore my entropy is going to be the log of the range. It's going to treat it as a uniform distribution. As I increase the number of bins, I'm going to capture the shape of the distribution. But I can keep increasing the number of bins until I have one bin per sample. And when I get to one bin per sample, I'm back to an uniform distribution, a discrete uniform distribution, which is log of the number of samples. So the smoothing that you have to do in order to get the right amount of smoothness from the sample in order to estimate the entropy correctly is very sensitive to the procedure that you use for smoothing. If you put too many bins, you can get a wrong answer. If you get too few bins, you can get a wrong answer. And the complaint about what was causing the problems in the information bottleneck paper was that this issue was not properly taken into account when they were calculating the information, the mutual information metrics. You could make the mutual information anything you wanted just by changing the bin size.
Hoshin, I have two more comments, but as time is already, we're quite past this 1 hour, we can either do that later. Leila, you decide.
I guess people are leaving as they need to. So if people are staying on, I assume it's because they're interested.
Absolutely, yes. We
Okay.
can save.
So one comment is about how you could do your quantile approach on 2D data. And I wonder if it doesn't work relatively simple. Maybe I can share my screen when you unshare yours to draw a picture.
That would be great. Thank you.
Probably I'm making the same mistake as you did. But let's see. So let's assume these are the two axes and you have your data points somewhere in here. Huh? So this is your x min, x max, y min, y max. So you'd start here and you'd start looking around what is the closest point, which would be that one. And that would be the probability mass that belongs to that point. Yeah, the probability of unexceedance. So from here, you'd move on in increments of either x or y and see in which direction comes the closest point. And the spacing,
I like the way you're going. Yes.
So it's, you know, percent of x min, x max that you're going in x and y direction. So it's kind of a normalized distance in both direction. So you'd maybe, let's say there's another point here. That's the second point. So here, the additional area that comes into play is maybe this area here. And that's the probability mass, sorry, that's the x delta y product, the area that belongs to the second point.
Okay.
And then from here, you'd go on, what is the closest point from here? Maybe it's this one. So you get a dx, dy, that's dy, dx, and that's the area in between these, the previous and this point, and so on. So this is, and by the increasing number of points that you add, that's your probability. And some of them are your quantiles, whatever quantiles you choose to take. And these are the areas, and this takes into account the, you know, the relative position in x and y direction.
And then you bootstrap on the sample when you do this. So
exactly,
you bootstrap the sample,
then because you get different points, these kind of rectangular areas will look different each time. Wouldn't
I like
that
it.
be the equivalent?
Yeah.
May I have a hi?
Please.
Hi, Mary.
Hi, that's great. I just was wondering how condition looking for the closer point is conditioned by the minimum point, because it depends where is your minimum point is going to shape the next nearest point, right?
Yeah, just like in the one-dimensional case, let's say this is one-dimensional and these are the locations of your points. You start at the first and then to the second, to the third, and these are the distances, and that's your probabilities of unexceedance just by counting the points from the smallest to the largest.
Yeah, I like the analogy. It's one I had not thought of. Full marks for that. I think it's worth developing and testing. It makes perfect sense. Yeah.
Okay. One potential issue is that the scaling of the axes relative to each other influences which point is closest, but maybe that's a minor thing. But right, you can stretch one of the axes.
If you move on to the right and in x direction in increments of, say, always 1% of the x min, x max range, and at the same time 1% in the y min, y max range.
Yeah, I was going to say the same thing in a different way and say that basically it's relative to the total area, right? So you take your largest point, your extreme point, and that's the total area, and then this area is relative to that total area. So there should be a way to normalize it so that it's not dependent on scale. Wow.
Okay, and I have
great idea.
One more comment that goes back to the very beginning, where we're talking about negative entropies. I kept thinking about this. So for discrete cases, my interpretation, or maybe an interpretation of negative entropy, is if the answer that you get from someone contains the question you have asked, but even more. So for example, you're rolling a dice and you just want to know if it's even or odd, yeah? But someone tells you it's a 3. So if we think of this, of entropy again as numbers of questions in the questioning tree, someone gives you an answer that solves a question, a more detailed question, but a question that includes yours, the answer to yours. So one node, one branch higher up in the questioning tree. So in that sense, the information you got from this 3 has a certain information content coming from the probability distribution of 1, 2, 3, 4, 5, 6. So that's the surprise. That's the question you were spared. But actually you were asking something else. You were just asking, is it even or odd, which requires less questions. So in that sense, receiving the 3 for you is over information. So you have negative entropy. Yeah, you know more than you need to know about is it even or odd. Maybe this is a possible interpretation of negative entropies. I don't know.
There is one other important consideration for this. So we get negative entropies for continuous distribution. So for a discrete distribution, the probability has a bound. It can't be greater than 1 and has to be greater than 0. But when you have a continuous probability distribution function, the value of the continuous probability distribution function at any point can exceed 1, right? Because you have a density function. So the only time the probability density makes sense is f of x times delta x. That's because the probability density is, I mean, the probability is not defined at a point. It's only defined at a finite interval delta x. So essentially, to deal with probabilities, not probability densities, but probabilities, you have to quantize the function. And that's the only time it makes sense to do that. So when you quantize the function, I think that negative probability situation disappears.
It does, yeah.
So the problem comes not so much about the interpretation from the person. I mean, I have to think about what you said, Uwe, but I think the big part is that this PDF function can take values greater than 1.
Yeah, if you look at the discrete to continuous conversion, it involves that log delta x, right? So delta x is the precision term. Yeah.
Right.
So maybe it's the same case here. You get an answer from a continuous distribution that is overly precise to a degree of precision that you don't even need.
Exactly.
That's wild speculation now.
No. That's actually the interpretation that Gongwei used in his paper when he said, if you want to estimate the entropy of streamflow, we want to estimate mutual information, but we're going to do it to 2 decimal points or to 1 decimal point or something like that. You actually take that into account so that you don't get a peculiar number, right? A peculiar interpretation, because otherwise the amount of information you need to provide is essentially infinite, right? Mutual information goes to infinity, and that doesn't make sense. But if I say I'm going to estimate streamflow to 10.1 or to the first decimal point, to the second decimal point, I'm now explicitly specifying the number of yes/no questions I have to ask in order to pin it down, and that's a finite number. It's a finite number of bits. It's a finite entropy.
Yeah. So that issue of yes/no question works only if there is some quantization, some discretization in there.
Yeah, because again, if you change the unit for a river to cubic kilometers per second, then you get small numbers and high densities in those numbers, and you get negative entropy. So I have a hard time believing that it's related to the precision. It's because the precision can still be the same, right? If you change the units and you just round to values.
So
yeah, but precision is relative to scaling, right? So.
Yeah.
So also the situation is that this problem arises only if you're trying to estimate the entropy, but not so much the mutual information in there. The problem abates quickly when you do the mutual information.
I have a quick question to Uwe. So regarding your interpretation of the negative entropy. So do you think that, so as you said, it is likely to be, you're answering more than what's asked for. But so that additional part of the answer, do you think the information that part is providing can be redundant or can also be actually relevant? So do you think even though that answer is, if it is redundant, do you think that will still can be interpreted as negative entropy, or that will not affect the sign of that?
Sorry, Roy, can you say that again? I lost my.
I'm sorry. So I was saying that. So in this case, let's say you have been asked to give an answer, but you're actually answering more than what's asked for. Now that additional part of the answer can be redundant, or it can be actually relevant as well. So do you think, depending on whether it's relevant or redundant, that will have an impact on the sign of entropy. Or if it is, let's say, redundant, then the sign will not be impacted by that additional information, even though you're answering more than what's asked for.
I think it really has to do with the relation of these of the answer you get and the question you're interested in. These negative entropies, I think, can only occur when the question you're interested in is a subset, a higher order node. Can you see this? The yes. PowerPoint?
Yep.
Okay, I just have to remove the picture. So it will only work. Let's say these are the precise answers on, guessing the 1, 2, 3s, and 4s. This is the question tree for it. And maybe someone tells you it's a 1, 2, 3, or 4, but you're only interested in, is it even or odd? That would be the setting. And only if this relation among what you're interested in and the answer you get, what you're interested in is a higher order branch in the question tree, then I think negative entropies can occur. If the additional information you get is, say, something completely else, if someone says it's a 1 and the weather is nice, then this may not hold.
I actually do think we're talking about two different things, because mathematically, if you just look at the equations, negative entropy comes about as a result of going from discrete to continuous, right? And you add the log delta term, and that delta is always relative to the scale, right? So it's always the delta precision term is always relative to the scale, because you can change the entropy to be anything you want by changing the scale. So if delta x in the log delta x is less than 1, then it's negative, relative. You're taking away entropy. So I'm not convinced that that's a direct thing. However, let's think about mutual information. Let's say that my uncertainty about something was a certain amount of entropy, and now I tell you something else, and it makes my uncertainty worse. Right. So now mutual information, by definition, has become negative. Okay, but that's a peculiar situation.
Mutual information doesn't suffer from this negative thing, and I think we are probably over-interpreting the negative entropy beyond what we just talked about, that the PDF can have values greater than 1 at a particular point in there.
It's true that it's true that mutual information can't be negative, but I'm just pointing out that you can have a situation in real life. Mutual information is defined as h of y minus h of y given x, right? But the assumption is that x contains consistent information about y. And if I give you a piece of information and it makes your uncertainty worse, that's not accounted for in this equation because it doesn't obey Bayes' law. Yeah.
That's only if the piece of information.
So it's going to reduce the mutual information in this case. I mean, the actual value can still be positive?
By definition, mutual information is only positive. But if I write h of y minus h of y given x, I can get a negative number under some circumstances. But the reason I can get a negative number is because I'm now violating Bayes' law.
But you can get a negative number for a specific value of y, but the mutual information is defined as an average over the PDF, and that will go away. So even though you get...
Yeah, I think it has to do with, like, if someone gives you information in terms of a probability statement, and you take that probability statement as face value, then you can have such a thing as sort of negative information on average. But if you just say, if you make your own PDF based on frequencies, basically, then you cannot have any uninformative information. It's with forecasting, like whatever the weather forecaster says if he makes certain statements each time and I build my own experience from that, at worst, I don't gain any information from that. However, if the forecaster says there's 10% of rain, chance of rain tomorrow, and I take that at face value, and that forecaster is really bad, in that case, I can have an increase of uncertainty on average, because I'm not building my own PDF, but I'm taking probability statements from someone else that might not be self-consistent.
Because I'm violating the fact that I'm assuming that the world is consistent.
Yeah.
So Bayes' law is assuming that the world is consistent. Good things to think about.
Yeah, super interesting. I think this will be very useful.
All right. So if you think it's okay, we can leave it there. Thanks so much, Hoshin, for the great explanation and discussion of your paper. So thank you. And our next meeting is going to be on February 24, and Professor Kumar is going to be showing his recent research too.
Thanks, Leila. Could you send me the link of the video so I could download that? Yeah.
Absolutely. Yes. This video is going to be posted on the YouTube channel too, so everyone can see it there. Thank you so much, everyone, for joining today. See you next time.
Bye.
Bye.